continue the discussion from where we left in the last lecture. So, we were looking at this 854-fold acceleration which is observed during the isotope electrocyclization reaction when you start with this particular substrate, and it gives rise to this particular product. And it has been observed that when R1 is equal to hydrogen and R2 equal to isopropyl and R3 equal to hydrogen. So, in that case we will have this hydrogen here and isopropyl here. So, this creates a chiral center. So, this is kind of induction of an asymmetric carbon atom into the organic scaffold. And in this particular reaction with these substituents, 854-fold acceleration in the rate was observed and high turnover frequency. So, we can now take up some discrete examples further with respect to these applications now. So, let us look at Fujita's octahedral and square pyramidal cage. So, I represent the octahedral cage as A and the square pyramidal cage as B. Let us once go back. So, this is the PD6L4 12 plus, this is a cationic cage where you can see the 4 different ligands. This is the L ligand. So, one on this face, one on this face, one on this and one on this, and 6 palladium centers. The corresponding square pyramidal cage has the corresponding L4 ligands again at the 1, 2, 3, 4 faces. We have the palladium centers at this particular vertex 1, 2, 3, 4, and then there is one palladium center for this particular face, and then another palladium center for this particular face. So, overall there are 6 palladium centers. That is, again it gives the PD6L4 12 plus macrocyclic cage. Square pyramidal cage, you see that this is open from the top face, whereas Fujita's octahedral cage is having this kind of an arrangement. So, Fujita's octahedral and square pyramidal cage were used for the catalysis of Diels Alder reaction, which is a very popular reaction in organic chemistry, and in this case the reaction is done in these molecular containers. So, let us look at this particular reaction where we have these substrates. We have NPH, and in the presence of first deuterium oxide at 80 degrees centigrade, in the presence of the supramolecular cage A, which functions as a supramolecular catalyst, we have the formation of the following product. In the second step, we have at room temperature, and this gives rise to the formation of this product C. Whereas, if you actually do the reaction in D2O at room temperature in the presence of 10 mole% of B. So, now we, instead of A, we are taking 10 mole% of B. It gives rise to the other regioisomer. So, this is a case of regioselective reaction, where when you take the Fujita's octahedral A cage, it gives rise to the unusual regioisomer. And also it is interesting to see that there exist pi stacking interactions between the host and the substrate. So there are pi stacking interactions between this substrate with the corresponding pi surfaces of the Fujita's octahedral cage. So that kind of interactions, non-covalent interactions, bring the molecules into the close proximity of reacting, leading to the formation of the unusual regioisomer. And what has also been observed is the retention of the product inside the octahedron. So once the reaction is over, there is retention of product inside the octahedral cage. And to circumvent this problem, the reaction was now done in the presence of 10 mole% of P, which actually led to the quantitative conversion to this product D. So the reaction of the 9-hydroxyl anthracene with the N-phenyl hexyl malimide actually led to the formation of the desired products. So what happens is that when you have the square pyramidal cage, so in case of B you have the square pyramidal cage, and the square pyramidal cage, you see it is actually, it is open from the top and it has got a bigger cavity. So the substrates can easily move into this particular cage and then easily come out. And also what happens is that the product formation actually removes the planarity of anthracene core. It removes the planarity of the anthracene moiety, and it facilitates the release of this product into the bulk. So now you see that the anthracene has lost its aromaticity, the product is easily released, and that increases the efficiency of the process and also the catalytic turnover. So overall we see now that because the loss of this planarity and aromaticity, the association of the anthracene with the pi surface of the ligand of the Fujita's cage is reduced, and therefore the release of the product can take place easily. As you can see in case of D also, the planarity of anthracene has been removed, and that facilitates the easy removal of the product into the bulk. Along the same lines, we can also have, so this is the first application. The second application is the Knoevenagel condensation catalyzed by supramolecular coordination cage. Again here we are doing this reaction with Meldrum's acid. We are doing this condensation reaction in the presence of 1 mole% of A Fujita's cage, water, room temperature 6 hours, it leads to 96% yield of the desired product. And the desired product is a condensation reaction where the following product was obtained. And when this catalyst, supramolecular catalyst, the reaction barrel the cavity was not utilized, then the yield was less than 10% in absence of catalyst. And in order to complete the procedure, the reaction was also done with the supramolecular coordination cage B. It was observed that the reaction goes slowly. Therefore, we observe that even with the same set of reactants and identical reaction conditions, the nature of the supramolecular cage and the geometry of the supramolecular cage plays a very important role in the desired outcome of the reaction. So, the geometrical restraints in the cavity control the reaction outcome. So, it is also important to keep in mind that whereas in the previous reaction the square pyramidal cage facilitated the reaction because there was a problem of inhibition, product inhibition once formed with the cage, that was overcome by using the square pyramidal B. But now in Knoevenagel condensation, the supramolecular coordination cage B does not perform satisfactorily. The next example we would like to consider here is the rate enhancement in the 1,3 dipolar cycloaddition reactions, and this was done using the following. So, this is the reactant, we have this as my starting material, and we can now have two possibilities. In the first case, we can have the following possibility, we can have this, and so this will give rise to the corresponding NH3 So, this will give rise to the corresponding 5-membered ring which is N. This is the triazole product, and this triazole product was actually this reaction was done in Cucur butyryl 6. So, this molecular barrel was utilized to do the cycloaddition reaction, and Cucur butyryls have a strong affinity for these protonated ammonium species because the cation pi interactions there is a strong affinity, and overall with the presence of these hosts there is the rate enhancement is 5.5 into 10 to the power 4 fold increase in the rate. So, we get this particular product. The possibility of the other product is also there, but here we have so the other product okay. Sorry, this is on this much. So, now we can have here again the reaction where so we can have this reaction which leads us to So, this is the other possibility. Now, this reaction does not take place, it is this particular reaction which takes place, and it leads to the formation of a regio selective product. and thus cucurbiturials function as molecular catalyst which promote these particular reactions. The next reaction we would like to investigate is the acid catalyzed Nazarov cyclization, where what was observed is a 1,000,000-fold rate enhancement in a GFO-L6 12- capsule. So, we have already looked at the structure of the GFO-L6 capsule, and we are now looking at the acid catalyzed Nazarov cyclization, and in this you have the gallium centers here, and the reaction takes place within the cavity. So, you have the now this is my OH group. So, these are my pentadinols, 1,3-pentadinols. These give rise to the cyclopentadienes. Now, in the presence of an acid, I am not going to draw the cavity again. It is understood that this process takes place within the cavity. You have the formation of this particular product, you have the formation of this particular species, and now it will undergo the rearrangement where it will give rise to and the starting material actually has the methyl here. So, methyl is here and the methyl is here, methyl is here, methyl is here. So, this carbocation is being stabilized now by the electron donating plus I effect as well as hyperconjugation, and we can now the proton will be lost. So, it will give rise to the corresponding methyl cyclopentadiene, and once this host, now interestingly, as you can see, this is an anionic supramolecular cage and it gives rise to a cationic species. So, the cationic species is electrostatically stabilized in this anionic cage, and the transition state is such that is formed very easily now, because you can see that the product is very closely related to the structure of the transition state, which involves this particular delocalization of the positive charge, and you can see that it goes by this particular process where the positive charge is stabilized over the different centers. So, this transition state is now easily achieved, and therefore, this particular supramolecular cage is able to lower the activation energy necessary to form to take the reaction across this transition state and form the product. But what happens is that now the catalyst, that is a supramolecular cage, binds with this particular product binding happens, and because of this product inhibition, the catalyst suffers from the product inhibition. Now, what we do is that this is now a diene and we add a dienophile. The dienophile, once it is added, NHCO, then it undergoes the Diels Alder reaction and gives you the final product. So, the product, because it is now it binds with the supramolecular cage, it has to be removed. Now, it can be removed easily by adding a dienophile with which it reacts and therefore forms the Diels Alder adduct. The Diels Alder adduct which is formed is this one NH, and we have got the stereochemistry here is not defined, but we have the methyls, the 4 methyls. So, this particular product is formed. So, so finally, we see that this diene is expelled from the tetrahedral cavity by reaction with the dienophile to give you the final reaction product. So, we can see this Nazarov cyclization is easily templated via this gallium capsule which promotes this reaction. Now, we can go to another example of the effect of a cage. So, just like a cage, as we saw in a previous case, can be used to enhance the rate of the reaction, a cage can also function as reaction inhibitors. The supramolecular cages can function as reaction inhibitors, and this was demonstrated by the group of Professor Nishk, NITCHK, Nishk group, who actually designed a water soluble Fe4L6 cage -4, which functions as a supramolecular protecting group. This is a so just like you have got protecting groups of the covalent kind in organic transformation, this Fe4L6 cage functions as supramolecular protecting group. Why? Because it prevents the reaction, that is the Diels Alder reaction between furan plus maleimide. Okay. So now what happens is that let us look at this cage. This is my supramolecular cage, and here we have got SO3 minus, that makes it soluble. So, this will bind here, this will coordinate here, this will coordinate here, and this will coordinate here. So, we will have 6 such ligands on the 6 edges 1, 2, 3, 4, 5 and 6. So, this particular supramolecular cage, now if it functions as supramolecular protecting group, because if you take furan and add maleimide, then no reaction actually takes place. There is no reaction which actually happens, because the furan is now present inside this particular cage. Okay, and it is not there is a strong association between this furan and this cage, and therefore maleimide is not able to now perform the reaction with it. But now when you add benzene, what it does, it displaces the furan. So now we have benzene which goes into this and furan is displaced, and this can now react with your dienophile to give you the classical Diels Alder product, right. So this is the product. So there are a lot of interesting things which can be done with these kind of cages by changing the nature of the ligands. So compared to the gallium cage, this is a very different kind of ligand is present, and so essentially furan gets tightly held here inside this, but then when you put benzene, it gets displayed and the reaction proceeds satisfactorily. Now we can look at the next application where we can talk about induction of chirality into the molecule, and this was again done by Fujita. So we have now the enantiomer selective transformation by Fujita. Again, this work was done again using Fujita's octahedral cage, but the cage has now been modified. Let us look at this cage. In the Fujita's cage, what we had was this palladium center was achiral, but now we have created the chirality at the palladium center. So in the octahedral cage, what we now have at the palladium center is as follows. We have taken a chiral ligand, okay, and you have ET, H, ET, and therefore you have the chirality here on the backbone, and so the chirality is coming here from the palladium side, that is the chiral center, and this is used to actually bring about the Diels Alder reaction between we have the starting material and we are treating it now with this particular reagent in the presence of water at 25 degrees centigrade and light. We call this octahedral cage as E. In the presence of E, we are able to get the following product. So the reaction takes place at this particular double bond. So okay, so you can see very clearly that the reaction is taking place at this particular center, and these are the two covalent bonds which are formed, which form the four-membered ring. So this actually is the first metal ligand coordination cage applied for an enantioselective reaction. Okay, this is Fujita's first metal ligand coordination cage which is applied for a enantioselective reaction. So now in the presence of this kind of a molecular cage, we were able to successfully demonstrate. Thus 2 plus 2 photo addition reaction was demonstrated successfully. Okay. So, you can see now that with this kind of a chiral cage, where the chirality comes from the backbone of the cage, although the previously reported cages, that is the A and the B, these are not chiral, these are not chiral. So, this is the chiral cage, and this created the chiral compounds. The chirality was introduced via successful 2 plus 2 photocycloaddition reactions. Okay. So, with this we come to the end of this lecture. In the next lecture, we will take up some more exciting examples of organic transformations which are mediated by the supramolecular reaction vessels. Thank you.